This video is an introduction to exponential equations. I'd like you to start by graphing the following data from this table. When you're graphing these points, keep in mind that each xy pair is an ordered pair and could be written this way. With the fractions, you'll want to estimate. And I know that they will be very close, and that's okay. Pause the video and complete your graph. Now, restart again when you're done plotting these points. So you should have a graph that looks the way this one does. And if you take a smooth curve and connect your dots, I want you to notice that the pattern here doesn't really indicate that this curve is going to go below the x-axis. And if you look at your numbers, you see your fractions get larger on the denominator, which means that we're going to keep getting a number closer and closer to 0, but we're never quite going to reach it. And so it's hard to draw that, but this doesn't actually go below 0. And so we have something that looks like this. Now, I want to ask you a few questions. Let's start just at the top of the screen here. You might notice the pattern doesn't form a line. What does it form? We would say it forms a curve. Okay, so this is an example of the graph of an exponential function. It's a big word. Practice saying it. Say it correctly. Exponential is the word. All exponential curves have this basic shape. Now they might sort of be flattened out or made taller and narrower. Well, looks taller and narrower. They might even be flipped over. But the basic shape of this curve is the same. I want you to pick 2 points from the table or the graph, whatever way you want, and I want you to find slope. If you use the table, you'll use the slope formula, the difference in the y's over the difference in the x's. And if you use the graph, you can pick 2 points on the curve and count rise over run to get from one point to the other. Pause the video and do that for 2 points right now. Okay, so my 2 points were 0, 1, and 1, 2. I took them right from the table. And when I did, 2 minus 1 was 1, and that went on top, and 1 minus 0 is 1, and that went on the bottom, and so my slope is 1. Now your 2 points might have been different, and you might notice your answer probably isn't the same. Let's do this again. Let's pick 2 different points, or you can even compare your answer to someone who picked different points from you. Mine might be different than yours. Find the slope of these points, and if you're finding your own, pause the video now and do that. My other 2 points were 2, 4, and 3, 8. And this for these 2 points is 4. What do you notice about finding slope using 2 points on a curve? You might notice that we get a different answer depending on which 2 points we pick. Is this true if you use different points to find the slope for a line? I want you to think about this now. You have found slope for many, many lines. Does it matter which points I pick? It doesn't. And so on a curve, your slope will be different based on the points you pick. On a line, it doesn't matter which points you pick, the slope will always be the same. So the basic rule here is that exponential functions have what's called variable slopes. Variable. It means they change. Vary means change. Sometimes we call these variable rates of change. Rate of change is just slope. Let's compare the basic features of the familiar linear with the unfamiliar exponential. And you'll want to copy this table because it gives you a lot of great comparisons that help you to see the difference with what you know about a linear equation and what's different about that in an exponential equation. So for the rate of change, or the slope, in a linear equation, the slope is constant. No matter what points we pick, we'll always get the same slope if we're looking at the same line. In an exponential function, the rate of change is variable. It's a fraction or decimal or percent of some number. And so it's not a number all by itself. It might be changing by 30% of something each time, or it might be doubling each time. Whatever is happening, the number doesn't have meaning without it being a fraction, decimal, percent of something else. The shape of a linear function is a line, while the shape of an exponential function is a curve. You're all familiar with the equation format y equals mx plus b for a linear equation. Well, for an exponential equation, the basic format is y equals capital A, and then in parentheses we have an r to the power of t. Now in the next row here, I give you what's called parameters. Parameters are just the things that define the equation, because they could really use any letters in these spaces here, m's, b's, a's, r's, t's. But what we're saying is, in this one, we're agreeing that m is slope and b is the y-intercept. Well, for an exponential equation, we're saying that capital A is the initial value, r is the rate, and t is time. And if this is graphed, then t would become an x. That's where our x would go, because the time changes. And so the last row here shows you the graph of an example. And so this is an example of a linear equation, in this case y equals x, sort of the simplest linear equation. And this is the graph of an example of an exponential equation. And this particular one is the graph of y equals 2 to the power of x. Look at what makes an exponential equation called an exponential equation. Look where the x is. The x is in the exponent, thus exponential. All right, so knowing all of these things, let's look at some relationships and decide whether they're linear or exponential. Now, before you answer the questions, you need to think about the rate that it's changing. Is it changing by a certain amount every time, or is it variable? Is it changing by some fraction, decimal, or percent of some number? That's the difference. Now let's look back at these. The ant population increases by 10,000 each month. Does it change from month to month? Is it always 10,000? Well, according to this it is, which means that this relationship is linear. Let's look at the next one. The rabbit population increases by 30% each month. So is that increase happening by a certain number every month, like the last one did? What we have here is a percent. So percent of what is the question? If the rabbit population is increasing, we're taking 30% of some number one month, and then we're taking 30% of a bigger number the next month, and an even bigger number the month after that. So our change is going to be a different number every time, and that makes this exponential. And so notice the rate of change here is a percent, not just a plain number. You try C, D, and E. Go ahead and pause the video, and when you come back, we'll see how you did. $10 in a piggy bank each month. The change is constant, $10 every month. It's linear. Earning 3% interest annually, 3% of the balance. Well, the balance could change every month because the 3% from the last month then went in. And so this one is exponential. And I'll just abbreviate. The last one says radio sales dropped 22% annually over the last 5 years. I made this one up. I have no idea what radio sales dropped or didn't over the last 5 years. But if it's 22% that it's changing, is that a linear or an exponential relationship? It's exponential because it's a percent of some number, and that number will change from year to year. There's two basic types of exponential equations, and they are growth and decay. So the one here on the left is an example of what a growth exponential equation looks like, or exponential growth. And you'll notice as x gets bigger, y is also getting bigger. It's the whole thing is walking uphill. As x increases, y also increases. For exponential decay, as you go from left to right, as x increases, what's happening to y, the height of the graph? It's decreasing, and of course I have it written here. But remember what we talked about. If you walk the curve or the line or whatever the graph is you're looking at from left to right, you're saying as x increases, what are you doing? If you're going downhill, then you're decreasing. And so here's decay and here's growth. The equation looks a little different when we put in the growth factor or decay factor. When we separate out the decay or growth rate, which is this R, from the whole growth factor or decay factor. Whatever's in the parentheses here, the base for this exponent, if it's bigger than 1, because 1 is added to it right here, it's a growth equation. But if you notice here, whatever answer is to this power, it'll be a number between 0 and 1. It'll be a number less than 1 because it's 1 take away something. And so that's going to be decay. We'll look at some examples of that, but I sort of want to give you a general overview right now. Let's take a look at a few slides and just practice growth or decay. The graph on the left, is it growth or decay? I hope you said decay. As I walk from left to right, the graph goes down. It is decaying. As x increases, y decreases. The graph on the right is growth. Whoops. I don't know what that just did. As x increases, as I'm walking along the graph, x is increasing, and what's happening? The height is also increasing. And so that's growth. On the next screen is the example of what the different equations look like. So I said if it's 1 plus something in the parentheses, and that is definitely more than 1, we have growth. What about this one? Well, if I was doing 1 plus some number, I certainly wouldn't get 1/2 as an answer. But if I was doing 1 minus some number, I could get 1/2 as an answer, and so this would be decay. So if what's in here is between 0 and 1, it's decay, and if what's in those parentheses is a number greater than 1, it is growth. The next one are word problems. We have increasing by 30% each month, growth or decay. The word increase, oh, this is doing all kinds of weird things, is growth. Sales dropped 22% annually. Is that growth or decay if it drops? Decay. So look, word problems, easy to decide. Increase, growth. Dropping or decreasing, decay.